Hello, everyone. Welcome to another MMO Development R&D session. Here we're going to be kicking off session number 11 with Mr. Nelson Lakay. Hey, Nelson, thank you for joining us.
Hey.
So this session is going to focus on the World Data Storage System. For many of you that have been following along with the MMO development videos, you've probably heard this numerous times referred to as the Persistent System by Lee. The idea was to have some sort of system that would facilitate the saving out of vertex information into files that could then be retrieved by an editor system where an artist could then manipulate vertex data, and as that vertex data is manipulated, it then gets saved back into this database system that we're going to be creating. Now, the first thing I'd like to just get out there is that I have absolutely no idea of how this is all going to be put together. And I think that's a good thing, because as we work our way through this, or as Nelson works his way through this, I can ask all sorts of questions just to make sure that I'm clear on what is going on, and hopefully that will help some of you that are following along as well. Now, Nelson, when we first started looking at, or when you and Lee first started looking at having to store this information, this vertex information, to a computer, you had talked about the possibility of two different methods. One, using a relational database system, or two, a file-based system, correct?
Yeah. So we went over, the differences because our DBMSs obviously already exist and have been written and vetted and everything. That was a consideration. But the issue with them is that they're generally designed to consume as much memory and as many spare cycles that they can in order to build indexes and other sort of optimizations, things that would interfere with a game running inside of Unity. We wanted something straightforward and lightweight that didn't consume a bunch of resources outside of what we needed it to do. We also needed it to store any amounts of arbitrary data, or by any I mean, as a really big number.
Right.
Of records of any arbitrary data. And so, yeah, we elected to go for a file system, or a custom database format,
and even
our DBMS.
And even with that approach, there were a few different discussions of, should we use, a file for every single patch, or should we look at using one very large file? Do you remember some of those discussions?
Yeah, we played around with the idea of leveraging the file system itself in order to help indexes and lookups to individual records, but we determined that it was a bit too unreliable. We needed something consistent, because Windows itself does its own indexing behind the scenes of your file system to figure out how quickly it can go to different paths. So we wanted we wanted something consistent that we didn't have to, that wouldn't cause intermittent issues.
Okay, now,
so we came up with this.
So what kind of intermittent issues could we have been looking at if we would have been doing individual files for things like every patch in the terrain?
Well, once you get to a certain large amount of files in a folder, particularly Windows Explorer starts to break down. And the indexing that the operating system does behind the scenes would change the performance that we get from accessing those different files depending on how much is indexed.
Gotcha. Now, you did some tests working with the multiple file approach, didn't you?
I did some tests, but I can't remember any concrete numbers.
Yeah, I do remember you doing tests, though. And it seems like you did have some issues, and you were definitely concerned with performance. And I also remember you saying your poor hard drive. But that's about all I can recall. That was a couple of months ago.
Yeah, well, that messed it up.
So now what you guys have, or what you ended up moving on to, is this two-file approach, correct?
Yes.
So go ahead and talk a little bit about what is this mentality or this method that we're going to be using.
So basically, we have this main database file, and then we have this index file, and database file, index file. There.
Okay.
The idea is we don't want to do an ON lookup on the database file to find particular records, meaning we don't want to start, okay, record 0, is this the record we're looking for? Then go to the next record, is this the record we're looking for? And if that's not the record, go to the next record, and so on. Because once you get, a few 100,000 records, that becomes very, very slow.
Right.
So what we have is this index file. And how in depth are you wanting me to say
Well,
this diagram?
because I think if I add a little bit more to the discussion right here, you can explain this a little bit more. And that is with the database itself, everybody that's been following along up to this point has been following along with the creation of this terrain system. Now, this database file that you're talking about, this whole world data storage system, doesn't store just patches. It can store anything, right?
Right. Basically, we needed a system that was indexed by coordinates, by the patch coordinates, that could store any arbitrary type of data, things like mobs or texture data or height data for patches and stuff like that, which gave us, yeah.
Yeah, so basically, the records that could be stored within the database itself could be of all sorts of different types, not just your standard patch record that's going to contain all of your vertices, your tangent data, etc. Correct?
Right. We can store virtually anything that's indexed by two coordinates. Basically, what I have is each record is represented with a class. And then any particular coordinate, so for example, 0, 0, can contain any amounts of different types of records.
Yeah, you could say at coordinate 0, 0, we could have a patch record. We could, and even then, with just the patch record, you've got layers as well. So we could say, let's look at layer 0 or layer 1 at coordinate 0, 0. So the patch for that particular coordinate, we could look at whatever particular layer we wanted and extract that data out. Then we could turn around and have, like you said, mob data. So we could have mob records. And we could say, well, give me the mob data for patch 0, 0. And again, all of this information's got to be stored in this database file, this one, what will end up being a giant file. But as you can see, I mean, we're going to have all these different types of records that could be stored in there.
Right, which presents the obvious problem of the even if we have an index, there's no way to absolutely locate every single different type and every single different layer of a particular coordinate, because obviously the different types of patch or different types, depending on how many of a particular type and depending on what types of records that you put for a particular coordinate, you're going to have variable size segments of this database. There's no way to absolutely reference any one of these objects.
Right. Just because they're very easily different sizes. So you need some way to be able to access something that could be deep into the database file itself, but you need to be able to access it quickly.
Oh, right.
And since we do have these different record types, you needed to come up with some means in which to get to the data that you needed quickly. So now here comes the index file. So I think now with our viewers, Nelson, understanding that we could have multiple records of the same type at the same coordinate, but with different layers, and we can also have different types of records as well. I think now you can explain a little bit more in depth about the index file and how that's going to be used just generally in getting to a record.
Right. Well, the index file is essentially going to be a file that contains 64-bit integers.
Okay.
Just back-to-back 64-bit integers. So we can absolutely reference any 64-bit integer within this index file. And those integers are going to be these, what are these represented in these black boxes?
So the 100, 500, 1,000, so on?
Right.
Okay.
Now we have the coordinates. And this is kind of a, that was a terrible line.
That was fine. Oh, look at you.
So we have these coordinates. So let's say we're looking for a record at coordinate 0, 1.
Okay.
So we take the coordinate 0, 1, and we run it through a function. And I don't pretend to understand the math behind the function.
But you know it, but it works.
I know it works. I vetted it quite a bit to make sure that it was consistently workable. It has something to do with spirals. I don't know.
It's good. It's good.
The interesting property about this function, though, is that given two integers, given an xy position, it'll spit out a number. And the interesting thing about that number is the further away from the origin the bigger the number gets. So the closer to the origin, the closer to 0, 0, the smaller the number gets. And another important thing is that it uniquely identifies every single coordinate that I could throw at it when I was vetting it.
Okay.
So what that allows us to do is take this coordinate 0, 1 and run it through the function, and we get this 2. And I don't know if 2 is actually what comes out of the function for 0, 1, but this is just a example. So we get this other number, and I call this the index.
Okay.
Which makes sense if you think about it, because this 2 is the index within the index file that contains the index to
the data within the database file.
Yes, to the data within the database file. So yeah.
Okay. You still there?
Yes.
Okay. Yeah, that makes sense.
So that's the index file.
So the number that gets produced, I mean, that is obviously that's just going to be referring to a byte position.
You're gonna have to multiply it by
Correct.
8.
But again, that's what we're going to use to get our offset within the file, right?
Right, and because the index file is just a bunch of 64-bit integers back to back, we can use that to randomly select that information out of the file.
Correct. Now this function is basically giving us this number back that we can then use to multiply by and find this offset. So I take it that the number is logical in such a way that there's no big gaps. Like you said, that 2 may not really be a 2, but there's no kinds of, because I could see where that could result in you wanting to store something out and it resulting in some huge number, and that's going to be the byte location, well, multiplied, of course, but then that would represent a large file, correct?
Right. There are gaps.
Okay.
They're not substantial, though.
Okay.
At least to the extent that Lee decided was good enough for how far this index needs to be.
Okay.
How big this index needs to be. Obviously, if you were only to store one patch, and that patch happened to be at coordinate 50,000, 50,000, the number that this function is going to spit out is going to be pretty big.
Right.
And then that big number is going to then allocate this index file to be a few gigabytes or even more.
Okay.
Just to get to that index location, or the index location within the index file.
Okay. And just so that no one gets confused looking at this and thinks, wow, well, that's just a sequential thing. You know, why is it such a big deal that you have to actually run this through a function with some sort of special math to spit back a number? Remember, we're dealing with a coordinate system here where we're going out in both positive and negative, in x and in the z direction, or x and y if we just want to look at it in 2D space. So you end up with coordinates like 0. It's not like a growing thing with 0, 0, 0, 1. Like Nelson has demonstrated here, you've got 1, 1, 1, 0, negative 1, 0. And so all sorts of very interesting number combinations. So it's not like a sequentially growing linear set of numbers that starts at 0, 1, 2, 3.
Oh, no. And then that presents the issue, because
Right.
how do we uniquely identify 1, 0, and 0, 1?
Exactly. Yeah, I was just wanting to say that in case somebody was making the mistake of looking at this and saying, well, it's just a sequential file anyways. I mean, well, it's still kind of tricky because we are dealing with these coordinates. And that's how we have to find some way to represent them in a sequential nature. And that's what you've done with that formula. Okay, so now with the index, we can then look into the file and we can get the information that is sitting right there, which is this the 64-bit integer. So now if you want to talk about that.
Okay, so this is the record list start. And this number right here.
I know you love Photoshop so much.
I'm not a designer. This 500, what it represents is the first record in the database file that is representative of 0, 1, of the coordinate 0, 1.
Now, does that have to deal with of that type or just?
No, period.
Okay. So that's okay, perfect. So that's the first record in the database. Okay, at that coordinate.
Yep. Obviously, we couldn't, because like we said, there could be 10 records
Exactly.
on the first patch, but 20 records on the other. There's no way to randomly select that data out of an index file. And if we allowed the index file to like let's say we list all of the possible indices for this particular coordinate. What would happen is, and what if we go ahead and add another patch record to the first index? We're now going to have to resize a 2-3 gigabyte file.
Correct.
And that's just going to be obnoxious.
Right. All right, so we're now pointing to the first record in the database file here at 500, which of some type.
Of any type,
That's right.
of any layer.
Exactly. So of some type. We don't, right now we're just pointing to that first record.
Yep.
Okay, so go ahead and, so underline, there you go, perfect. Love it. Ooh, such a sexy arrow too. Okay, so now what?
So now we're looking at a record inside the database file. And each one of these records, and I don't know why I didn't represent it here, but each one of these records has a header. And that header is a fixed amount of, well, it's actually not a fixed amount. I'll talk about that later. It's a relatively fixed amount of bytes, something that we can read in very quickly. And that header contains information like what type is this patch and what layer is it at. Most importantly, that header also specifies a next. So what we can do is we can say, okay, let's say we're looking for simple record on layer 2.
And just so that everyone's following along, right now what Nelson has depicted with this picture are two different types of records, a patch record and a simple record. So two different types. Right.
And this is the record we want to get to right here with that awesome circle.
Okay.
So we start off by we're looking for a simple record layer 2 coordinate 01. Like we've already started the index file, we've got the 500, so we're now looking at a patch record on layer 1. Our code is going to read in the header and determine, is this a simple record? No. Is this the right layer? No. Does this record have a next pointer? And that's the most important question, because once it figures out if it has an X pointer, which in this case it does, an X pointer of 700, what it's going to do is it's going to jump to the next record at this coordinate.
That's right.
And then it's going to repeat the process. So is this a simple record? No. Does it have a next? Yes. So now we're going to jump to index 1000 in the database. Now we're looking at this record. Is it a simple record? Yes. Is it on layer 2? Yes. We found our data.
Okay, beautiful. Now, obviously, as our artists begin working with the data, so let's say we use a world terrain generation system, we write all of this data out, it's now being stored in this world data storage system here, and then an artist comes along and they're working in some zone within the terrain, and they're sculpting or painting textures or whatever, and we are retrieving data from the database so that it's all laid out. Now, they're in there sculpting, and these changes need to be saved back into the database. So if you want to talk just a second about information getting written back to the database.
Well, there's a few different, saving back data is a bit more complicated. The first step is that we go to the index file and we say, is there a record? And I just want to point out that sometimes these squares are blank. And I'm going to represent that with a -1.
Okay.
Meaning there's no record for the coordinate 10. Because the first question that the database is going to ask the index, is there even a record for 01, for example?
Okay.
And if there isn't, then it's going to append that record at the end of the database file. Then it's going to tell the index, okay, this is now the new first coordinate of the first record for 01.
Gotcha.
The second case is if there is already a record here, we're basically going to do this again. We're going to find in this chain if that record that we're trying to save already exists. If it does, there's another two cases for if it does. Let's say we're trying to overwrite a patch record for layer 1, so we find it the first go. The next question is the record we're trying to save bigger than the record that already exists? If no, just overwrite the data right here. Nothing else needs to change.
Okay.
Does that make sense?
Yeah, absolutely.
If it's not, if it is bigger, then what you're going to have to do is delete this,
which is going to leave a hole.
Which is going to leave a hole. Go ahead and create or copy this essentially over here. And if my duplicate doesn't, Just imagine there's another record right here.
See, you shouldn't have been saying bad things about Photoshop. It hurt you.
So now we're basically going to move this guy over here, but then we have to update the index again. We have to tell the index that there's a new location for this patch record.
Right.
Now the second or the third case, what case am I on? The n+1 case is if we get to the end of the list and there's no record already saved of this type or of this type and of this layer, then all we do is add a new record at the end of it and then set the next of the last record to the new index here. And finally, the last case is if the record that we find is in the middle of a chain. And if we have to move it, if we can't just overwrite the data because it's the same size, if we have to move it, so let's say we take this, we move it over here, we're going to have to update the next pointer from the last record.
Right.
To reflect the new location.
Exactly. But now, as people can see, that when you're moving information around, we're leaving holes.
Right.
So then we end up in a situation where our database has now become fragmented.
Yep.
So want to talk a second about that? Because that's something we're going to have to deal with, right?
Yeah, defragging is actually pretty simple. The biggest issue is that you can't actively use the system as it's being defragmented unless we, I don't know, do some lock stuff. I hadn't actually really considered that before. We could probably figure out a way to do it. But essentially, how to defragment the system is pretty straightforward. All we have to do is ask the index for the first location of every record it has, then start walking those chains, and then start copying that data into a new file without holes, and then updating the index.
Correct.
So it's a pretty straightforward process.
Right. Let's see. Any other? Oh, corruption. You also are going to deal with corruption. You want to talk about that for a second?
Yes. The header of every record is going to have a checksum, and that checksum is simply going to be the MD5 hash of the data in that record, of the bytes of the data in that record. Every time we retrieve data, we're going to see if that record is corrupt or not.
Okay.
And if that we will also implement a method that will walk through every single record and find any corrupted data just for a general maintenance thing. Other than that, I think the last issue is versioning.
Okay.
Which I haven't mentioned yet. Versioning is going to be pretty straightforward. In the header, every single record is going to have a version. Now, if you were ever to change the data format of that record and you already have production data in existence, the issue of converting that data into the new format is going to be a problem. In order to fix that, all you have to do is in your load methods for each of your records, be aware of what version the current record is. And then if you were to add a new version, you would just add a conditional. If the data we're loading is version 1, do this logic. If it's version 2, do that logic, blah, blah, blah. And then next time it gets saved out, it's going to be saved out in the proper format.
Exactly. Okay, very cool. Now, one other thing that we're going to introduce that's going to become pretty important is unit tests. We're going to be doing testing throughout this development, right?
Yeah, for a system like this with such a simple API, writing automated tests becomes very important, especially as we start playing around with the innards of the database. We want to always make sure that we didn't break anything.
Exactly.
And during development of the system, it was immensely helpful to have that sort of warning if you did something wrong that messed up something that you hadn't considered before.
So I wanted to point that out. We will be spending a few minutes talking about how we will be approaching unit tests. We'll be using NUnit. And let's see, what else? Anything else I can think of? Oh, of course, by the time Nelson gets to the end of this, for testing everything out, we'll just write some outside of the unit test, of course. We can just write a simple console app that utilizes the system to store information and to retrieve information for verification purposes. Now, we're not worried about any sort of compatibility, if you will, with Lee's terrain system. Again, Nelson has designed this in such a way that, again, you just write a class that is going to represent a record type, and that record type can hold data however you need data to be held, in what fields, etc. So once this system is completely done, Then we begin looking at how we want to integrate this into the current state of the terrain system. But again, the nice thing is we will have this world data storage system that works off of coordinates that we can then use for retrieving information out of and storing information back into. So I just wanted to point that out, that we're not looking to get to the end of session 11 and be testing this out with the terrain system. Nelson will just write a very simple console app for storage and retrieval, just to prove above and beyond the test. It's a simple app for storing our own data in. So Nelson, is there anything else that you want to add in?
Well, no.
Okay, yeah, I think that covers it pretty good, and I now have a good idea. It's just nice to know that, you know, you've got an idea based off of what you and Lee have discussed previously in regards to how the patch record needs to be laid out, but we're not locked into stone at all to any of these record types. That can change later, and you've even taken into account what if we do indeed have production data in and we need to change a record type that already exists and has data stored with versioning, which is very cool. So I just wanted to make sure that that was presented and everyone knew that we're not stressing over that, because once we get done with this and then we go to turn around and implement it or make use of it with the systems that we've got in place, it's very easy to make this system accommodate whatever we need as far as information that gets stored. So thank you guys very much, and we will see you in the next video where we will get the project kicked off. Thanks a lot.